Hello everyone, in this lesson, we will continue to study the basic knowledge module. Now, let's learn the decomposition of signal. Typical deterministic signals introduced in the previous section are relatively simple signals. In engineering, the signals are often more complicated than that. In order to facilitate the study of signal transmission and processing, complex signals are often decomposed into sums of simple or basic signals. According to different methods of decomposition, signals can be decomposed into different components. Usually, there are the following methods: DC and AC component, even and odd component. Third, pulse component. Fourth, real and imaginary components. Next, orthogonal function component. And the last one, using fractal theory to describe the signal. This will be the content of the following lecture. First, let's start with DC and AC components. In the study of circuit and electronic circuit, we all know that processing method of DC signal and AC signal are completely different. Thus, for a signal input to the system, it's necessary to decompose it into DC and AC. Signal Ft in Figure 1 can be decomposed into DC component E and AC component FAT. The average power of the signal is equal to DC power plus AC power. The signal can also be decomposed into even and odd components. Obviously, the even components of the signal has even symmetry, and the odd component of the signal has odd symmetry. You can also use Formula 2 and Formula 3 to get even and odd components of a signal. The average power of the signal is also equal to even component power plus odd component power. Signal Ft can also express a superposition of many pulses, which is decomposed into pulse component. As shown in Figure 2, the width of the pulse is delta tau, and the height of the pulse is f tau, when t is equal to tau. The pulse can be expressed by Formula 4. When tau changes from negative infinity to positive infinity, Ft can express the superposition of many narrow pulses. As shown in Formula 5, if delta tau approaches 0, the incremental calculation in Formula 5 will be a differential operation. Here, this incremental calculation becomes delta t minus tau. The corresponding properties of epsilon t and delta t will be introduced in detail in the following lecture. If delta tau approaches 0, delta tau can be d tau. The summation operation can be an integral operation. Then Ft can be expressed by Formula 7. The next decomposition method, real and imaginary components. When signal's instantaneous value is complex, it can be decomposed into the sum of real component and imaginary component. Of course, the real and imaginary components of a signal can be solved through calculation of signal Ft and its conjugate complex function. The signals generated in practice are real signals. The properties of real signals can be studied with the help of complex signals. Let's move on to orthogonal function component. If a set of orthogonal functions is used to represent a signal, then the components that make up the signal are orthogonal to each other. Decomposing signal into orthogonal function components play a very important role in signal and system theory. This is the key points of this course. We will learn it in the frequency domain analysis module of continuous system. To sum up, today we mainly learn the content of signal decomposition, including signal DC and AC decomposition, decomposition of even and odd components, decomposition of pulse components, decomposition of real and imaginary components, decomposition of orthogonal function, as well as the method of describing signals through fractal theory, which will be discussed in the following lecture. So much for today. Thanks for your attention. Goodbye.